Modeling swelling kinetics and transport in hydrogels using mesoscale simulations is coming from Georgia Tech.
Yeah, thank you very much for the introduction. So I will talk about the working questions, how we model hydrogels and polymer networks. But before that, let me briefly tell you about some other projects we are working on, just to give you an overview. Doesn't work?
Just check it.
Check it. This is my phone. Okay. Does it work now? Okay. No, I cannot hear anything. So we're doing computational modeling, and these are kind of some examples of the work we're doing. Say we look in the thermocapillary flows when we try to understand how we can use non-uniform heating to transport fluids. Say thermocapillary waves we create by heating the substrate. We're looking at surfaces with some structures, fancy structures, for example. We look at the surfaces covered with flexible elastic cilia, right? And this problem we try to, for example, control motion of small particles, microparticles, and microchannels, and create surfaces that can either trap particles or levitate particles, right? So some anti-falling surfaces. We look at microswimmers. Essentially, the question here for this project was to if we have a gel that can oscillate, change volume, how we use it to actuate a swimmer that can self-propel in a microchannel, right? So it's low Reynolds number flow, so you need to create some time reversible motion. So we look at these. We look at the flapping and swimming, which is at larger. It's not 0 Reynolds number, but it's still small Reynolds number. So it's maybe like a fly or some small fish. And here is, for example, an elastic wing or kind of plate that oscillates and creates some very complicated flow structure. So we try to understand how the elasticity plays, what's role elasticity plays in swimming and flapping at the regimes where viscosity is important as inertia, right? We look at the actuated surfaces. So it's kind of similar to this story when you have surface covered with some elastic filament that can be actuated by some external forces. And again, we try to understand how we can use these surfaces to manipulate particles, for example, or mix fluids, or enhance heat transfer, all these kind of engineering problems. We did a lot of research on understanding the particles, so motion of particles in microchannels. And this is, for example, we can see like elastic particles that go through a narrow constriction. And here what we did essentially, we try to understand how we can separate particles or cells. It's actually the main reason we try to detect cancer cells by mechanical stiffness. So we want to separate, say, stiff particles versus soft particles, because cancer cells, they're soft. And if we can do it in high throughput in microchannel, then we can essentially detect the cancer cells, right? And we did also research on polymer network, and that's essentially the topic I will tell you today. So we model polymer networks, and we try to understand how to model polymer networks. Okay. So for today, I will tell you about polymer networks. And polymer networks, they are very common material, right? So it's essentially polymers that are interconnected, that can be physically interconnected, chemically interconnected. Whatever I will show you today is more relevant to chemically interconnected networks, so they are kind of permanently linked. And they can be natural. For example, we saw a few talks about cytoskeleton. This is a beautiful example of polymer network. Or they can be synthetic hydrogels. Again, we have it in many different engineering systems. When we have these hydrogels, properties are, if we talk about transport properties, they're very highly permeable. So the porosity of these materials is large. It can be up to 98%, so it's almost entire solvent, right? It can be maybe in 70s, this is kind of low limit. At the same time, they are very elastic, right? So we can stretch it hundreds of percent. They can be deformable, and they can still support mechanical load. So, for example, in our body joints, we have layer of hydrogel that help us to reduce the friction if we bend, I don't know, a knee, right? And what is also very nice about these materials, they're typically sensitive to environmental stimuli. For example, if we change temperature, we can change pH, we can use light, and then this material starts swelling or deswelling. And at the same time, he will change the volume maybe 10 times. So it can be a large change in volume, and this is controlled by external stimuli, right? So this makes these materials very interesting or very attractive if we want to use it in some engineering systems, right? For example, for drug delivery, we can think about the system in which we have this material that we trigger some, I don't know, heat, and then we release the drug in a very specific location, right? So it's used for tissue engineering, for example. It's a scaffold in which we can grow some other tissues. It can be used also for smart robotics, soft robotics, what is called these days. So when you have some material that is soft, but it's responsive, so you can control it, you can make some robot that is really small and can handle very tiny particles, right? But if we want to use this material for these applications, what we really need to know is how to model this material, because this is usually very nonlinear material, and then it has a bunch of different processes that take place at the same time. There's transport processes, there are mechanical processes. So how to model this? This is essentially the question we try to answer in our research, right? And this model should be mesoscale because, well, on one side we want to capture the effect of internal structure, right? It is a network that can be deformed, that has some internal structure, which essentially control the transport for this network, which is important, again, for our applications. On the other hand, we want to look at the systems that are relatively large, so we can essentially model systems that are relevant to our engineering applications, right? So we kind of, in mesoscale, we want to capture things that are internal structure, represent the internal structure. On the other hand, we want to model relatively large systems. So we use dissipative particle dynamics, which is a mesoscale computational method. So this is kind of nice diagram showing a bunch of methods, and DPD is here, which is in the between continuum method and atomistic methods, right? So we in atomistic methods, we should model everything, all the interactions we have in the system, but in that case, we're very limited to the size and time scale. We can essentially simulate using even fast today's computers, supercomputers. On the other hand, if we use continuum methods, we need to have some assumptions about transport coefficients in the system, which apparently depend on this internal structure, and we don't know them. Right, so we are in between. We use dissipative particle dynamics, which is the particle-based method. So essentially, you can think about it as a coarse-grained molecular dynamics. So we have particles that interact, and there are two ways we coarse-grain these particles. First, each DPD bead represents a bunch of molecules, right? Or even maybe better to say it's representing some small volume of fluid, right? And then this volume of fluid, a bunch of the molecules, they interact between each other. So we reduce the number of molecules we need to model and track. And we also coarse-grain it in the way we replace Lennard-Jones potential that we use in MD with a soft potential, which is essentially linear potential, which is shown here. And this potential is soft, so the time step we can use is much larger than we would need to use in MD. Right. So these two things help us to drastically increase the time, the system time we can model using this method. The method actually based on three forces. It includes three forces. So again, these are forces that act on each DPD particle, and this is Newton's equation of motion that we need to calculate to track the evolution of each particle. So it's pretty much the same what we would do in molecular dynamics. Now the forces we have, they are repulsive force, which is essentially conservative force, and this is given by this linear potential, so it's soft force. The second force is drag force, essentially dissipative force that mimics viscous drag in the system, and this one is proportional to the relative velocity between DPD particles, right? So we can introduce viscosity in the system this way. And the third force is essentially a random force, stochastic force, which give us temperature in the system, or maintain the temperature in the system. So essentially these two are related to each other for dissipation theorem. And the important thing about the DPD, which actually what makes it very useful for our applications, these all forces, they are pairwise, meaning that all forces always act on two particles, right? So what it gives us that the momentum in the system is exactly conserved, right? So if momentum is conserved, this system will always reproduce hydrodynamic behavior, even if we have a relatively small number of molecules or particles in the system, right? So this is very important. This is what's so-called DPD thermostat. Essentially, these two forces, they constitute the DPD thermostat. And if you look at the literature, there's use for this. We can, for example, replace this conservative force with Leonard-Jones and then use this DPD thermostat to model real atomistic systems. But again, the main advantage is this is momentum conservative thermostat, which help us if we want to model hydrodynamic systems. Yeah?
Sorry, then the direction of your stochastic force is not random.
It is between the particles, right?
It is determined by the position of the drag, not completely stochastically.
The value is random, right? So, but it's isothermal essentially. So if you look at the temperature, you track the temperature. Okay, so this is the model. Now, let me talk about how we can use it to. So we can model, for example, polymer chains. We can model particles, and we do it the same way as we would do it in molecular dynamics. So we essentially take these beads, DPD beads, and connect them using springs, right? So DPD itself in the solvent, we don't have any attraction. It's only a purely repulsive system. Now, if we want to form a chain, we just connect these beads using linear springs, so thin springs, and we can also add bending interactions. So if we want to introduce some bending rigidity, right? So this is, for example, a filament that is composed of bending springs between each three beads and stretching springs between each two beads, right? So this filament has both bending rigidity and stretching rigidity. If we want to have some rigid particles, we can just cluster DPD beads and keep their relative position constant. So this will mimic rigid body, and we can characterize it typically by measuring its hydrodynamic diameter. Right? We can put it in DPD fluid and see what's the drag force, so we can calculate the hydrodynamic diameter, and that's characteristic for the size for the system. Right? For polymer chains, of course, we can calculate, for example, radius of gyration. We can put it in the solvent again and see what's the radius of this structure. This can help us to characterize the system. Okay, so how we model our polymer networks. So essentially, this is a polymer network that we build, and it's relatively simple structure. So essentially, we have these filaments, right, that I showed you in the previous slide. So each of these filaments is composed of these DPD beads connected by bending and stretching springs. Right? So it's essentially a bunch of beads that are connected, and they are also interconnected to form this random network. Okay? So this is the whole idea. So now how we generate this network, this is relatively easy way of doing it. So if you actually think about like a real experiment, when you synthesize a gel, you put a bunch of molecules, they somehow equilibrate, then you add cross-linker, and then they will cross-link and interconnect these polymers, and then you get the network. So we essentially do it in the opposite way. We start with cross-linkers. We start with points that essentially cross-link points for our filaments. We distribute it randomly in the space, so we can control how they distribute it, right? And then what we do, we connect these crosslink points with the neighbors by filaments, and we keep the average connectivity of this network whatever we want, right? So we have a control over these two important parameters that characterize network. So crosslink density and number of and average connectivity, right? So crosslink density tells how many points, how many crosslinks we have per unit volume, and average connectivity tells to how many crosslink points each crosslink point is connected. Okay? So there are two parameters essentially for our model, and these are two examples of the network we generated. This is different number of crosslink points and connectivity, and you see that structure is really different. What is identical for both of them? This is porosity, which represents the volume of void in the network to the total volume, and this is 81% in both cases. And actually what I will show you in the next few slides, that if we talk about transport properties, this is the parameter that essentially defines the transport, not the structure of the network itself, but the porosity of the network. Okay, so we have this network. It is elastic network. It can be deformed. It has porosity, whatever we have for normal gels. Now, the first thing we wanted to validate that we can reproduce transport properties using this network, right? And to validate this, we did several simulations when we looked at the permeability for this network and diffusivity of this network, right? So diffusivity, we look at self-diffusivity, diffusivity of rigid particles, and diffusivity of polymer chains. And let me start with permeability. So here, we essentially take this network and impose a fluid flow for this network and measure the drag force, right? So we plotted here, it's normalized by the diameter of the filament as a function of porosity. Now this each point here, it is a different network with different number of crosslink points and average connectivity, right? So there's 18 different networks, if I remember correctly. And we see that we plot it as a function of porosity, and it doesn't matter what's exactly the structure inside. As soon as we plot it as a function of porosity, they all nicely collapse to the same master curve that actually tells us that internal structure is not important as soon as we have the same porosity in the network, right? This is random network, so internal structure does not play much role, and we can reproduce. This is paper. This is essentially theory, and this is red line. We're very close. We have a little bit different coefficients, but we're really close to whatever the theory predicts. And this theory, of course, was validated by experiments, so we can reproduce the dependence of permeability on network porosity with our model. So the next thing we can look at essentially diffusion of particles. So here we look at the diffusion of rigid particles. They are characterized by hydrodynamic diameter. And we will look at essentially cell diffusion. So it is a DPD particle itself that constitutes the solvent, how it moves through this network. And these are clusters of, I think it's 6 particles. This, I don't remember how many. It's 12 or 6 particles. So again, if we plot all the data, though, so again, each point represents different network, we see that they are only function of porosity, right? Same as we see in experiments. It's not a function of internal structure. Of course, in the limit that pore size is large enough so we don't have this trapping effect in the network, right? So if we go to that limit, we will see effect of structure. But as soon as we're larger, then they all independent of the internal structure. And we can also compare it with hydrodynamic scaling theory, which is, this is the expression that theory gives us. And essentially, this is an exponent that we can measure from our simulations. And this is experiments that give exactly the same exponent. So essentially, all these curves, they with the same expression, the only difference is the radius, or hydraulic radius of the particle that we can measure independently. And we can see we can nicely reproduce the theoretical result. and actually experimental exponent, we can capture it too using our model. So we're happy to see this. Then we looked at the polymer chains. This is a similar story. We just put polymer chains inside, and we can measure this exponent. We got a 0.75. Experiments show 0.8. Again, very good agreement, very close agreement. One interesting thing is that actually if we take polymer chains with the same radius of gyration as particle, we see that chains diffuse faster, right? Which actually, according to the theory, should not happen, right? Because everything is defined by the radius. And the reason is that as the polymer chain is located inside the network, the actual radius of gyration of the chain will change because of the network, because of the confinement. So we can measure it here. We can see as porosity goes down, then the real hydrodynamic radius also decreases because of the effect of the network itself, and that's actually explain why they can diffuse better. They can essentially go through the network by rotating in a sense. Okay, so we were happy to validate. We see that our model can reproduce diffusion, so we can, again, so the model itself give us polymeric network, which is elastic, right? So what next we try to do, we try to see what happens to these transport properties if we deform the network, right? So in what I show you here, so we take this network and essentially stretch it. We stretch it such that the volume is conserved, the porosity stays the same, but this internal structure changes, right? And what I show here is each point is permeability, right? Which is normalized by permeability in the undeformed state. And this point give us values for 18 networks we modeled, right? So this is, each one is the average of 18 different networks. And what we see that for all these cases, they all essentially collapse nicely in one curve, right? Which essentially different permeability, give us different permeability for direction along the stretching. So it is higher permeability along the direction we stretch the network and lower permeability in the direction normal to this stretching, right? So essentially what happens is that we take this network, which is random, we stretch it, our filaments orient in the direction of the stretching, and then there's easier flow in that direction, right? So the flow that has lower hydrodynamic resistance, and that's what we see as a larger permeability in this direction. So we create this anisotropic orientation in the network, which give us this change in permeability. So we can see it always increases in the direction of the stretching and decreases in the normal direction. This is essentially compression, so the meaning is the same, right? If we look at the diffusion, this is, again, similar trend. We can see that in the direction of stretching, we have a higher diffusion, so it's easier to diffuse in that direction. Normal to the stretching, it is lower diffusion. What is interesting is that the total diffusion, total diffusivity doesn't change. It stays the same, and there's actually recent experiments, they confirm it. They did actually with liquid crystals, they changed the orientation. They saw that indeed the total diffusion coefficient will not change, but it will change in different directions. We also look at what happens if you shear the network, right? So first was normal stresses, now we have shear stresses. We see here that permeability increases actually in both directions, kind of a little bit counterintuitive. In the direction normal to the stress, we see no change because essentially filaments rotate in this direction, in this plane, and does not change permeability. With self-diffusion, it's a little bit more complicated behavior, but again, we see this total doesn't change. Okay, so essentially what we see that permeability is a function of this orientation. So what we did next, we took this deformed network and calculated orientation tensor, and then we plotted all our results in terms of eigenvalues of this orientation tensor. And what we see here that all our data, so that was the original data, when we plotted in terms of eigenvalues of the orientation tensor, we see that everything collapsed very nicely and essentially it confirmed that this is the parameter that we need to look at. This is orientation inside the network that define the transport properties. So as soon as we know the orientation, doesn't matter how we deform the network, we know what happens to the transport properties. Okay, so I told you that our interest was actually to understand more engineering problems in the sense of, well, bioengineering in this case. So how we can use hydrogels or polymer network, responsive polymer network to for drug delivery applications, right? And this is a simple system we're looking at. So essentially we have a hydrogel capsule, right? So this is the same network I will show you before that I show we can model the transport properties. We have this network to build a capsule, right? So this is a cross-section, essentially two-dimensional. We put something inside, some sort of nanoparticles that mimic a drug, and we want to figure out how we can release these guys from inside this capsule in a controlled manner. Okay, so this is a very simple question that we want to try to answer. And this is a way to think about designing some drug delivery systems, some drug delivery agents. So again, so this is the same model I showed you before. What we did essentially, how we did this is a capsule already. So what we did, we took this network we had, we generated in bulk, and then we cut whatever we have out of the size or geometry of our interest. So we can create a sphere, we can create any shape we want this way, and it will be essentially composed from this highly porous network, right? So this is again our particle composed of this nice network. So we need, next step we need to introduce responsiveness to this network, right? So essentially what happens with a gel, if it swells, if you change something in an environment, so on chemical level, it's you sort of create internal stresses inside the network that try to elongate the filament, right? So they elongate the filament, and then the network essentially swells and expands, right? So the dynamic of this process, of this swelling, is defined by balance between two forces. One is elastic energy inside the network, which is a result of some chemical process. We don't want to model it, but we want to see the effect of this. And the second is drag force of the solvent that penetrates inside the network, right? And these two processes, they are balanced because it's slow dynamics, it's overdamped system, but it gives the kinetics of the volume change. So to model this volume transition, we do a very simple thing. We essentially just at the beginning, when we say, okay, we expose the gel to some stimulus, we change the equilibrium length of our filaments. So this way we introduce this elastic energy in the system and let this network relax, which essentially equivalent to the swelling in the physical system, right? So we don't model what exactly happens on the chemical level to these polymers, why they get this energy. We just introduce it there, and then we model the entire process that happens after it. So, and numerically, we just change the equilibrium length of these filaments that all we have inside the network, right? It's very easy to do. So we can validate this approach by comparing the swelling kinetics of the gel with experiments, and the theory actually show this theory here, and this is for a sphere. So this is spherical particle, this is Tanaka's model, and here we show how radius changes in time, right? So essentially this kinetics, as I told you, it's defined by the balance between elastic forces, which essentially modulus of the network, and the drag force on the filament, and this is given by this parameter d, which is the ratio of these two, which is collective diffusion, and this is the parameter that essentially characterizes the network, the gel, and this is characteristic time that tells how fast the gel will change. So these symbols represent our simulation result. This is the theory. It kind of matches very nicely, and we can calculate what's essentially the collective diffusion from these calculations, right? It's a little bit hard to calculate it based on properties of the network itself because we still have relatively small particle, and the surface is kind of affects the bulk properties. We can do the same with a hollow sphere, and again, these are experiments, simulations we did. This is line and experiments. Model, right? This is this model, and there are also a set of experiments. I didn't show it here, but it kind of fits nicely. So essentially, this simulation tell us that we not only capture the transport properties correctly, we also capture mechanical properties correctly, because this collective diffusion is a function of elasticity, function of modulus of the network, right? Essentially, it gives us the balance between elastic forces and transport properties. Okay, so we validated this part, so let me show you how we essentially can model the release. This is our model again. So this is a gel particle which we put polymer chains inside and nanoparticles. So we want to compare these two cases. So these chains that have a radius of gyration of 1, and this is in dPd units, and these particles, they're a little bit smaller, they have a radius of gyration 0.7. We put them inside, and initially we set the pore size in the network is a little bit smaller than the size of these particles in chains, so they cannot easily diffuse out. So essentially, they will stay inside these containers. Okay, and that's what you see in this simulation. So this is essentially a particle. It kind of fluctuates and oscillates, but the particles they're sitting inside, and this is cumulative release. So you can see maybe a couple chains manage to escape, but nothing actually can leave this gel. They stay inside. Now, the first thing we wanted to look at what happens if we swell this network. Okay, so this is simulation that show how the swelling process works. We see that the capsule increases in size. We see actually it goes through some kind of instability in the shape because it's a little bit buckles because it's swelling is relatively fast in this case. And then you can see that pore size in the network indeed increases as we swell the network, and we see this release of chains and release of particles. This was observed in experiments, so this is exactly what people see when they try to use a gel particle, put some drugs inside and swell it and see the release. This is diffusion-driven process. We can confirm it if we measure the release, cumulative release, and we see it is linear process, so it depends on the diffusion, so it's diffusion-driven process. Right, and we can indeed, if we measure the pore size, we see that the pore size is kind of comparable to the size of the particles, so we can pretty much easily understand what happens in this situation. So now, the next thing we try to do, we try to see, okay, we start with a gel that has pores that are really small, so there's nothing goes through these pores. What happens if we deswell this particle, right? We kind of say, okay, maybe nothing will happen at all. Well, we did a simulation. We figured out that there's a lot of particles go out, so it's very fast release. But indeed, the pore size goes down, right? So this is initial one, this is final size. So pore size decreases, but we still have a release which is very fast, actually. So it turns out that in this case, the release is not driven by the diffusion, but it is driven by the solvent that we push out of the capsule when we deswell it. So the volume decreases, solvent should go out, and essentially it is a fluid, so it goes through bigger pores, slower hydrodynamic resistance, and these bigger pores let this solvent to carry particles or chains out of the capsule very fast. Right? So it kind of helps to find bigger pores that are bigger enough for particles to go through, and then we have very fast release, which is completely defined by this hydrodynamics of the system. We can quantify it. You can see here that release is really fast, but it only happens during short time, which actually given by this volume transition time. So this is the time when the capsule deswells. Now, interesting thing is that chains, we have much larger release of chains, right? You remember with diffusion, chains were released in slower rate than particles because they have larger hydrodynamic, this radius of gyration than the particles. That was chains here. Now the release of the chains is large and the release of the particles is small. And the reason is that the particles, even if we have this flow, but the network deswells and pore decrease in size, and they're not small, too small for particles to pass through, right? So they kind of filter the particles, and they limit the release. So we have relatively small release of the particles from compared to the chains, right? If we actually see some sort of a jet of particles because there's like few larger pores that let these particles go through, and other they essentially block the motion. For these chains, there's no really, we cannot see that the release is limited because the chains essentially they can stretch and they go through the network, and then they can go through relatively small pores. It doesn't really matter for them what the size of the pore. They can elongate essentially and penetrate through the network. That's what we kind of cartoon to show what happens to the chains. Okay, so to help these poor particles, we thought, okay, so can we somehow keep this pore open? So what we did essentially, okay, say, let's introduce some constraint inside the capsule that will stretch this capsule as it diswells, and this stretching will create larger pores so the particles can escape. So what we did here, we took this capsule, this is the same capsule we had, we put micro rods inside, and then as capsule is diswelling, these rods essentially stretch the membrane, stretch the network, and have these pores open even as the gel diswells, right? The pores stay open, and they allow these particles to leave, so we can help to increase the release of the particles. And indeed, if we measure the release rate with rods and without rods, we see we increase it quite a bit. And this is because we have these larger pores stay open by mechanical stretching of the gel with these rods. Now, there's almost no effect on the chains, because for chains, pore size is not a limitation for the release. They can go through even small pores, doesn't matter if we stretch the membrane or not. So we can think about some simple scaling model that essentially explain what happens in this hydrodynamic release. We can think about some sort of effective Peclet number, which characterize the ratio of release by diffusion versus release by this volume change, hydrodynamic release. So essentially, diffusion coefficient we can easily measure in the simulations. So a release by hydrodynamic is essentially given by the change of volume of my capsule, right? Because the difference in the volume before the swelling and after the swelling, that's the solvent that leaves. And if we multiply it by the concentration inside, that's essentially give us a good estimate of how many particles we will release, right? And then if we compare it with the results for chains, this is what this model predicts, and that's what we see in the simulations for 150 versus for 20, very close agreement. So this indeed, that's what happens. So this is the release by this hydrodynamic process. If we want to compare it with particles, then we see good agreement of only if we add these rods. Without rods, I think it was 30. But again, this is tell us that the particles are essentially filtered by this membrane. So now, if we think about applications, this is very, very, very important. So we know exactly how much we can release from this capsule. And if we talk about drug delivery, I guess you want to know how much drug you will get from this capsule, right? So, and versus diffusive release, when it depends on how long it stays in the area until it completely everything is released, you don't have too much control. Here, as soon as the capsule diswells, it releases a bunch of drugs, and that's it, right? So we know exactly how much it was released. So this is a big difference versus release by diffusion that is people try to use now. So this method gives us much better control over the release rate. We can also think about pulsate release when we have several cycles. So each time we diswell it, we will have a bunch of released, which is again well characterized. So here, that's what we see. We have several cycles when we diswell, then we see no release. This is pulse that release, no release, then the next pulse of the release, then no release, and again. It kind of decreases each time because the concentration inside decreases, but again, we can control. We know each time we release what happens. Okay, so let me talk about another example we have like 5 minutes left, when we try to do something that is, in a sense, opposite to the previous example, right? So we wanted to try to design some artificial phagocyte, right? So phagocyte is a cell that eats something in our body, right? To try to protect us from viruses and kind of other stuff. So the question is how we can build a synthetic system that can eat something from the solvent, right? So when we talk about release, we have something initially inside the capsule, then it goes out. Here we have opposite problem. We want to capture something from the solvent and keep it inside our vesicle, right? So get inside our capsule. So what we do here, the idea is very simple. So we have these responsive gel particles, but now it is inside a lipid membrane. So this green stuff shows a lipid membrane. Again, this is cross-section, it's three-dimensional, and this is gel particle that can swell in this well that sit inside, right? And essentially, the goal is we have these molecules in a solvent, right? So everything is in the solvent here, that initially outside of this vesicle, we want to get it inside the vesicle, right? By some process. So physically, the people can build these kind of vesicles, composite vesicle. They have gel inside. This is an example from its Nature paper that essentially what they did. This is green, shows lipid membranes. Kind of occasionally it's the same green we use in the simulations for lipids. So this is green is the lipid membrane. And this reddish part is a gel that is loaded with some drugs. What they did in this paper, essentially when they perforate this membrane, their solvent goes inside, this gel swells and break completely the membrane, and they very fast release these drugs that are sitting inside this gel, right? So it's kind of, they use it for different purpose, but essentially the system has the same components what we want to use, so it is a lipid membrane and gel inside. There's a bunch of papers, if you look at the literature, they try to build it because they use it for cell mimetic, essentially models, so it is kind of simple models, so you can think about this as a cytoskeleton inside the lipid membrane. So people are very interested in the systems, but we want to use this idea to create essentially artificial phagocyte. So we have this lipid membrane. Let me briefly tell you what is the lipid membrane. So we have, in our model at least, so we have lipids that we construct from DPD beads. They have hydrophilic head. It's 3 beads, very simple, right? 2 tails, it's normal lipids heads, each one with 3 beads. So you can see already how much is the coarse grain compared to real lipids, which are much more complicated in terms of number of molecules here. Now these lipids, they self-assemble into a membrane. So this is a membrane, they self-assemble, this is in solvent. We actually pre-assemble it into a vesicle. So we use this is the vesicle we create. It is, we just pre-assemble them and put everything together. So it's, we start with this configuration. We want to wait till they self-assemble in this. Now, if we talk about membrane, so if we take a membrane and stretch it, then the stress will increase until the membrane breaks, right? If the stress is larger than yield stress, it will break, create a pore, and then this transient pore will essentially will keep the tension in the membrane constant, which is line tension in the membrane. So if we release the stress, then this line tension will close the pore. Okay, so this is essentially a reversible process. So we can stretch it, it will create a pore, then we release this membrane, pore closes, right? So we want to use it in our vesicle. That's why I tell you. So again, so this is the idea of the vesicle. So we have this gel inside, we have this lipid membrane outside. So what happens is, what we want to do, we want to swell this gel so it expands, fill this volume, create pressure or stretch the membrane breaks, create a pore, then part of this gel exposed to the solvent that is outside. Now, as it's exposed to the solvent, we say, okay, so let this gel be functionalized such that it binds to our target molecule, these red guys, so they can adsorb on the surface. Then we diswell back, we change the stimulus outside that causes the swelling, deswelling, this gel shrinks, and the pore closes, right? So this is the whole idea. So let me show you how it works. So here we see this gel swells, increases in volume, now the membrane breaks, and then this red guys diffuse and absorb on the surface, then the gel dissolves, and then this pore tries to close. It takes some time, but eventually it will close. Okay, here it is. It did close, right? So this is the process we can see from a side here. Again, it stretches the membrane. It not breaks immediately because it needs to build the pressure inside. It's still expanding. Then create this pore and allow the transport through the membrane essentially. And at the end, what we see is these red guys isolated inside the vesicle. So we mimic this process of kind of eating this system managed to eat these red guys, and this is kind of artificial phagocyte we try to design. So we have 3 steps in this process that I want to talk very briefly in a couple minutes. So first one is essentially how we break the membrane. Second is how we have this adsorption. And the third one is the closure, right? So how we close the pore. So pore formation is purely mechanical process, right? So we have the membrane stretched by the gel that swells. So as soon as the pressure created by the swollen gel exceeds the yield stress, right? We can easily estimate it. Then the pore will form, right? If we take the data from our calculation, so we can calculate, for example, energy, elastic energy, take the derivative, we can estimate the pressure created by the gel, and then we can compare it with the tension. Well, we can use it to calculate what tension it will create in the membrane. Then we can see that they're about the same, which means this is indeed the reason for this membrane to break, right? So it breaks because we create this pressure inside. So if we want to, so essentially there's 2 parameters that control this process. One is elasticity of the membrane, right? If we have a stiffer membrane, then it has more energy. It can easily break the, gel, then it can easily break the membrane. The second parameter is essentially how much this gel want to swell. So the swelling ratio, if they have a larger swelling ratio, again, we have larger energy accumulated inside that help us to break the membrane. Okay, so on the other hand, so the pore size is important because the pore size defines how fast we will absorb the molecules from the solvent, right? So larger pore size is better, but of course there's a limit because the pore is too large, then this guy will just leave inside from this membrane, that will disintegrate, and we will not be able to capture anything inside. We can do simple estimates based on the area of the lipid, so then the maximum radius of the gel after swelling is 1.4 of the radius of the vesicle. In this simulation we use 1.2, but you can see it's already kind of close to the situation where this lipid cover less than, well, almost half of the gel, so it's maybe kind of tricky part here because the gel can go out, right? Now this plot shows the how we capture the molecules over time. We can see it's pretty much linear process. Again, it tells us that this is purely diffusive process. It's driven by the concentration gradient and they adsorb on the surface. Interesting, then with this swell, this gel, there's some number of molecules that essentially detach because there's some solvent that goes out of the gel and essentially remove part of the molecule sitting on the surface, but still large number stays on the surface, and then it is essentially what's captured. And the final part of this process is membrane closing, right? It turns out this is the most difficult process in terms of to find the parameter that have the system work, because what happens is that this gel tends to go through this pore and essentially block the pore closure, right? So there's two physical mechanisms that cause this. One is essentially if we have a particle near a wall, there's a diffusion away from the wall, right? So hydrodynamic resistance closer to the wall is larger, so the diffusion will essentially go into direction away from the wall. It means into the open pore. The second one is as we close the vesicle, the solvent goes out and it's actually push the particle outside of the vesicle too. So if the vesicle starts here in the center, we can see that with time it's going closer to the pore, and the only method we found right now to deal with it is essentially you need to dissolve more, so the size of the particle is, so gel is smaller, so it takes more time to go to the pore, and then the pore have enough time to close, right? So this figure shows essentially how the pore size and gel size changes in time. So we start here swelling, it swells fast, reaches the wall or diameter of the vesicle, then at this point vesicle breaks, and you can see that the pore forms and increases, and it continues to swell till the final size, right? And there's the final size of the pore too, and then we deswell it, and then we see this slow closure of the pore of the lipid vesicle, right? So this is characterized the process, and there's difference in the time when the gel fills the vesicle and versus the vesicle breaks, because the still internal stresses grow as the gel continue to swell inside. Also, it doesn't change the diameter. Okay. Okay, I'm good on time, I guess, before the lunch. So let me just briefly summarize. So what I try to show you, so we have this model, we developed a model that we can use to model essentially transport processes in polymer networks and mechanics of the polymer networks, right? Like swirling kinetic of the polymer network. And this is one model that I can capture it. This is mesoscale, so we can go to model relatively large systems. We showed that we can use it, for example, to understand transverse and deformed networks. We looked at how we can use this model to model release from gel particle vesicles, right? It's not vesicle, it's gel capsule, right? Or we can use this model to design some sort of artificial phagocyte when we can essentially capture something from the solvent. And this we can use, for example, remove some viruses from the body, right? If we can functionalize, or we can just do some sampling in a very specific location. We can put these guys in our bloodstream and then tell them to capture when they passing some specific place, so you will know exactly where did you get this sample from, right? So it's very maybe interesting idea. Okay, the final thing I want to mention the students. Hassan, who was working on the first part of this story, he's a postdoc in NYU, and Ayuka and Kate, and the undergrads, they're working on this phagocyte story. Kind of works slow, but we need to get a paper out. Yeah, so in the fundings from ACSPRF for this research. Thank you for your attention.
Your algorithm preserves momentum, conserves momentum.
Right.
But then you obtain the permeability, which goes into the Darcy equation. And the Darcy equation does not
to measure permeability, we essentially create a flow by external force. We push the fluid through. There's a pressure gradient, essentially.
Yeah, so where the momentum...
yeah, it's just external. We add external force to create the momentum. So we essentially add the force to the network and to the solvent in the opposite direction, so they balance each other. So nothing goes... So the total momentum actually is conserved still. But we have a flow with respect to the network. But there's viscosity, so this energy is dissipated.
Just one point I didn't get right from the beginning. So you have the DPD to model the polymer network, and how do you model the solvent?
It's DPD, yeah. So the following this idea is DPD, this kind of classical DPD. So the network is essentially just DPD particles that are connected.
There are others that are then moving around.
Everything is interact with these DPD potentials, right? So this explicit solvent. So this is network with explicit solvent, and everything interacts these three forces for DPD we use, right? So we didn't do many modifications in this case.
later on in your applications, I mean, your polymer chains, I mean, there are many like micelles, or they can have different conformations or configurations when you apply external force of shearing or concentration, vary the concentration. That's something you cannot do in your model.
Yeah, we can do that. We essentially for the chains we have these DPD beads that are connected by springs, bending and stretching strings, so they give you internal elasticity of the chain, right? And then if you put it in a solvent, you can measure, for example, radius of gyration of the chain. So we actually the network we model with semi-flexible filaments, so they're kind of relatively stiff, right? But you can change it. You can also change. For example, to model this change that we want to capture, right? We can change the way they interact with other parts of the system. For example, with the gel, and then we create some effective attraction, right? So they will bind to the surface, right? So we don't have real attraction in the system, but we can reduce repulsion between these two parts of the system, between chains and the gel, and then they will attract to each other.
Did you compare this? I mean, certain polymers it's known certain configuration at certain.
Yeah, you can say lipids. You saw we have this head, tails, and this is. I mean, it's coarse grain, so it's not exactly what you would see for lipid membrane. For example, our membrane is kind of linear lipid membrane, almost incompressible. In this case, because you have soft potentials, it is compressible, right? But again, it depends what you want to mimic, right, or what you want to model. It is coarse graining. There's some pluses and minuses you need to take into account when you model it, but it can capture, say, rupture. Okay, we can capture it, right? So there's some phase separation, we can capture it. All these kind of processes, yeah, that's fine.
And also some like these worm-like micelles.
Yeah, you can form. I mean, I didn't show here, of course, but we can take a bunch of these lipids, put it inside, and see what kind of structure you will get. The problem is that you usually need a very long time for it and a very large system for it, right? So it's computationally very hard to do, but we did some studies like that. You can really see they form micelles, depends on the concentration.
And there are experiments on like threads of these micellar solutions, and if you apply some stress to it, the rupture is caused by the rupture of the chains, you know.
Well, rupture of the chains is a little bit different right here, because I mean you can also think about introducing the bonds that essentially, I mean, computation you can do this, right? So if you put a criteria when your chain is overstretched, then you just remove the bond. So it is also possible to do. We try to keep it simple. Okay, even keeping simple, it's not simple. So we try to understand for simple problems, then we can.
This is just a practical question. I mean, this pulsating is interesting, but how do you do it practically? I mean, you want to deliver a pulsating chemical. Now you put it in a gel, and now you have to deliver an agent to do that.
Well, I mean, you can cause this volume transition. For example, you can locally heat it, or you can use. So what's actually purely in experiments, they bind the gel with gold nanoparticles, and then they impose it like through magnetic field, and then they heat, and then they go through volume transition, right? So you can just give a pulse of this magnetic field, then they will swell, then remove it, this will, right? So you can do it multiple times. So it's completely reversible. There are a bunch of papers that they look at this. It's
in the body, if you're thinking of drug delivery.
Yeah, you can locally heat it, for example, right? So, or it can go through the air region where you have, say, large pH, and then it's changed this. But again, it will just one pulse. It will not release continuously. I know, I'm not doing real drugs. It's a computational, right?
No.
We'll find some experimentalists to do this, right? That's all their problem.
Questions? No, we thank the speaker again.
Thank you.